This is the screencast for section 6.4, example 2, the law of exponential change. This is going to relate back to pre-calculus and your compounding continuous interest. So first, let's take a look at how the calculus and pre-calculus relate. If y changes at a rate proportional to the amount present, so in other words, if dy dt equals k times y, now notice, that is dy dt equals k times y, the output, not x, the input, or t, the input. And if y equals y sub 0 when t equals 0, so that's your initial value, sort of, then y equals y sub 0, again your initial value, e to the kt, or you used to know that as a equals pe to the rt, so a is y, p is y sub 0. Again, y sub 0 is your initial value. E to the kt. So you have interest compounding continuously. So if the derivative equals a constant times your output variable, you are working with compounding continuous interest. The constant k is going to be your growth constant if k is greater than 0, or the decay constant if k is less than 0. Now, the process to show why those two are related is actually a process we're going to use quite a bit, so pay attention to this. I want to show that dy dt equals k times y implies that we're also working with y equals a e to the kt, compounding continuous interest. So first I have dy over dt, so I got to get the dt's on one side, and then k times y, so bring the y back over. Basically separate my variables. And I get 1 over y dy equals k times dt. So now I'm ready to integrate. The antiderivative of 1 over y is natural log of the absolute value of y, and then the antiderivative of constant with respect to t is going to be that constant then times t. So it's like the antiderivative of 5 is 5t. And then plus c. Now I'm trying to solve for y here, and y is trapped inside of a natural log of base e. So if you remember from pre-calc, one of the strategies we used to solve log equations was exponentiating. So I'm going to take the left side and raise it to a power with base e. And I'm also going to do the same thing for the right side and make that an exponent of e. I chose e because I want the base of my exponent to be e because the base of my log is e. So now I have y equals e to the kt times e to the c. Now, first of all, where did the absolute value go? Well, it's not trapped in the natural log anymore, so we don't need the absolute value. Y can be positive or negative. And then e to the kt times e to the c. Wasn't it supposed to be e to the kt plus c? Well, that's out here. It's kind of like if you have x squared times x cubed, that's x to the 2 plus 3. So I reversed it. If you're adding the exponents, it's the same thing as multiplying by the same base. So now, final answer, y equals a, basically we're calling e to the c our initial value a, e to the kt, or your y sub 0 e to the kt. So in summary, over here, if you have compounded continuous interest, a of t, so your final output is your initial value times e to the exponent of your rate times time. That means your differential equation then is dA dt equals r times a, the output. And then your initial condition is a sub 0, the amount of money you had at the very beginning. Now again, you're going to use this process in the future, not right away, but I wanted to show it to you now because I wanted you to see how dy dt equals k times y actually means you're dealing with compounding continuously interest, or interest that's being compounded continuously. Now example 2, I'm not sure how much you remember about pre-calc. This is definitely a pre-calculus review. Suppose you deposit $800 in an account that pays 6.3% annual interest. How much will you have 8 years later if the interest is A, compounded continuously, B, compounded quarterly? Well, compounding continuously is A equals PE to the RT, or your book is using A equals Y sub 0 E to the KT. Same thing. So our initial amount of money that we're investing is $800. The rate is 6.3%, and that's for 8 years. So the final amount of money I will have is $1,324.26. Part B asks for compounding quarterly. That's the other formula that you will use. A equals P times 1 plus r over k to the kt. Now, this formula can get used for quarterly, monthly, semi-annually, etc. That would just change your k value. So in this case, 800 is still our initial value. Our rate is 6.3%, but because we're compounding quarterly, our k value is a 4. And then that's for 8 years. And then that would be $1,319.07. Now these two formulas are actually the same. If you start out with A equals P times parentheses 1 plus R over K to the KT, so compounding monthly, daily, annually, whatever, you just change the K value. Well, what if we take K and make it approach infinity? So compounding continuously. Well, that's going to equal PE to the RT because the limit as x approaches infinity of 1 plus 1 over x to the x is E. So this inside portion right there is E, so it's PE to the RT. Then now try problem number 19. Says in exercises 19 and 20, find the amount of time required for a $2,000 investment to double if the annual interest rate R is compounded, annually, monthly, quarterly, and continuously. Fine. So let's start with part A. Annually, my k value, so the denominator here inside is going to be 1, and so is 1 in my exponent. So now I can divide both sides by 2,000. It really didn't matter how much you're investing. If you're doubling, you're trying to get your output equal to twice what your input was. And then simplified inside the parentheses. And now how do I solve for an exponent? Well, logs solve for exponents. So I take the log, the base of my exponent was 1.0475, so that's going to be the base of my log. Now logs find exponents, that's the whole point. So t became the output of this log expression, and then 2 is what I'm taking the log of. And then in my calculator using, see up here, log base, I found out that that was 14.94-ish years. If you have an 83, you got to use change of base formula. Part B, monthly. So again, 4,000 equals 2,000. Divide both sides by 2,000, and then you get your 2 equals. Now, the 1 plus, this is your rate over monthly. Your K value is going to be 12 to the 12 times T. And then I would simplify this like so. And then again, I'm solving for that exponent, so I got to change to log form. So log base, the base of my exponent, of 2 equals my exponent, 12t. Divide both sides by 12, and I get t equals about 14.62 years. So a little bit less, which is true, because the more you compound, the more interest you're going to make. So a little bit less than compounding annually would be compounding monthly. Quarterly should be somewhere between A and B's values. Quarterly, I'm done with the 4,000 equals 2,000 thing. So 2 equals 1 plus 0.0475 over 4. We're compounding quarterly, so your K value is 4. Again, you're solving for an exponent, so I'm going to pick log base, this whatever this combination worked out to be, 1.0011875 of 2 equals 4t. Logs find exponents. Divide both sides by 4, use my calculator, I got 14.67 years, which is between A and B. Good. Now part D asks for continuously. That is going to be the least amount of time because that will create the most amount of money. The more compounding, the better. Well, assuming you're saving money. So part D, 2 equals, again, your initial value is going to be 1 because we're just trying to double that. E to the RT. Logs solve for exponents, so I'm going to use log base E. So natural log of 2 equals my exponent, so 0.0475t. Divide both sides by 0.0475, and I get about 14.59 years, the least amount of time so far.